Assalamualaikum to all students. So I will continue on chapter 2, topic 2.3, vapor liquid equilibrium. So previously I already mentioned, or I already touched on the physical concept of the distillation process. So this is example of distillation column equilibrium concept. Okay. So what is vapor liquid equilibrium? So for example, if we have a distillation column here, so we have feed. So feed is in form of mixture. Okay, for example, if we have component A and B entering the distillation column, so there will be two types of product. So distillate and also bottom. Okay, bottom. Okay, so when the feed entering the distillation column, so we will heat up the mixture at certain temperature. So what happened in the column is the when we apply heat on the mixture, so the liquid will evaporate. Okay, so when it evaporates, it will turn into vapor. Okay, when a lot of vapor accumulate inside the container, so the vapor cannot go anywhere and it cannot escape. Okay, so the sufficient amount of vapor will accumulate inside the column. Okay, so when the accumulation of vapor happens, some or the portion of the vapor will begin to condense or to change into its liquid state, original liquid state. Okay, so when the vapor condense into the liquid and the liquid will still evaporate, so there are two types of process occur inside this column. So we call it as evaporation and also condensation. Okay, so when evaporation and condensation occurs at the same time or concurrently or continuously, so we have two types of rate. Okay, two types of process, condensation and evaporation. So in sufficient time, the rate of evaporation will be equal to the rate of condensation until when it's equal, it is already reached the equilibrium state. Okay, so that's why we have to study on vapor liquid equilibrium, because of when we separating the mixture. For example, if we have component A and B, both component A and B inside this column will exist as both vapor and also liquid. Okay, so it depends on temperature also. Okay, this is what I mentioned just now. So the rate of evaporation for component A is equal to the rate condensation of A. The rate evaporation for component B is equal to the rate of condensation of component B. Okay, which means in the distillation column we have okay, so component A and B will entering the column, so as a mixture. Okay, in the feed, so we will denote the mole fraction for A in form of liquid as XA. Okay, in liquid form. Okay, for component A, mole fraction for component A in gas we denote as YA. Okay, gas or vapor. Okay, there is actually XB and also YB, but when we separating one mixture from another, so we only focus on one parts of component, so we don't bother about B, because of the one that we want to separate, or our desired component is actually A, so we just focus on component A. Okay, so actually XB and YB is exists, okay, but we only calculate for XA and YA. Okay, vapor liquid equilibrium actually has been tabulated and has been studied, okay, and the data for the vapor liquid equilibrium is you can find in Paris Chemical Handbook, okay. So the vapor liquid equilibrium data, they and can also be predict and can also can be also be calculating, okay, by using two types of law, Rock's law and Dalton's law. Okay, later I will show you on those law. So this is example. If you open the Paris Chemical Handbook, so you go to the distillation chapter, okay, so you will find this type of table, okay. So in this table, for example, if you have two component A and B, okay, A, for example, if you have ethanol and B is water, so you want to separate ethanol and water. So the vapor liquid equilibrium data will show you the fraction of component A in at each temperature. Okay, so for example, if we have 99.5 degree C, the mole fraction of A in liquid, which is XA, is 0.0190. Okay, for the mole fraction of A in vapor, which is YA, the fraction is 0.1700. So this is how you translating this, or this is how you read the data. Okay, so this is also example of vapor liquid equilibrium data. For example, this is for hexane and octane system. So this is for benzene and toluene. So the data will be in terms of temperature and also mole fraction. This is mole fraction in liquid. This is mole fraction in gas. Okay, in respect with the temperature. Okay, when we plot the vapor liquid equilibrium data, so we will get this type of graph. Okay, so this is temperature, so this is the mole fraction. So the temperature versus the mole fraction. So the mole fraction, it can be YA or XA here. Okay, so when you plot, you will get two types of curve. It will become like this. Okay, so from this graph you can see that these two curves actually telling you something. Okay, so this curve, okay, up from this curve is the saturated vapor, or we call it as a dew point. Okay, so at the bottom here is the saturated liquid, or we call it as a bubble point. Okay, later I will show you what is definition of dew point and bubble point. Okay, another point is, as you can see here, okay, for example, okay, so for example, I have a distillation column here. So I have component A and B entering the column. So I heat up the column, the mixture. So the mixture will evaporate and will condense, evaporate and condense. So in this column, there are two types of state of matter, which is liquid plus vapor. Okay, so the vapor liquid equilibrium data for component A and B, okay, when we heat up, for example, at starting 70 degree to 120, okay, so at 70 degree, so this is the fraction of the fraction of XA and YA is 0 because of maybe the process hasn't started yet. Okay, so at temperature of 19, you can see here, okay, you can see here when we when we put a line here, okay, so this is where you can find the XA. Okay, when the line hit the saturated liquid, so when you go down, you can get the XA value, which means the mole fraction of A in liquid. Okay, and if you straight and you go to the another point, another curve, you hit another curve, okay, the saturated vapor curve, so you will get the YA data, the mole fraction of A in vapor. Okay, this is how you use this curve. Okay, so I just want to explain to you, okay, below this point, okay, below this curve is actually a liquid region, which means at this point, at this area, the component A exists as a liquid. Okay, so at this area within the curve, the component will exist as a mixture of liquid and vapor. Okay, so at the upper part out of the saturated vapor curve, so this is vapor region, means the component A exists as a vapor. Okay, very simple. And you must know that the mole fraction, this is actually basic. Okay, the mole fraction of A in liquid plus the mole fraction of B in liquid will be equal to 1. Okay, the summation of XA and XB. The same goes for YA and YB. Okay, so what is bubble point and what is dew point? So bubble point is the point where the liquid start to boil. Okay, so this is the bubble point, which means after the curve, up at the upper part of this curve, okay, the liquid will start to vaporize. Okay, okay, so okay, for dew point, so dew point here, so up at here, so below or above this curve, so this is point where the vapor start to condense. Okay, so inside this curve is actually a mixture of liquid and vapor. Okay, okay, what is Raoult's law? So Raoult's law is they take into consideration the partial pressure here. Okay, I think you can still remember, this is from the mass transfer equation. So the partial pressure of A is equal to XA times V. P is vapor pressure of A. Okay, or the total pressure of A. So for Dalton's law, partial pressure of A is equal to the vapor fraction, mole fraction of A in vapor times with the total pressure of the system. Okay, so it's slightly different between Raoult's law and Dalton's law. Okay, so if we manipulate both equation, Raoult's law and Dalton's law, okay, so another thing is, this is the total pressure, which means total pressure of the system is equal to the partial pressure of A and partial pressure of B. You sum and you get the total pressure here. Okay, so by manipulating the above two equations, so we can get the composition of XA and also YA. Okay, I will show you how you can manipulate this data. Okay, for Dalton's and Raoult's law, if we manipulate both of the equation, so we will get another equation. Okay, so this is for Raoult's law. So this is for Dalton's law. Okay, for Raoult's law, it considering the vapor pressure of pure A. Okay, so partial pressure of a small letter of P is equal to mole fraction of A in liquid times with P vapor pressure of A in pure A, okay, at certain temperature. So while for Dalton's law is equal to partial pressure of A small letter of P is equal to vapor fraction of A, okay, mole fraction of A in vapor times with the total temperature. Okay, so you must know that total pressure. Okay, the total pressure here is also equivalent to partial pressure of A plus partial pressure of B. Okay, so this is partial pressure, so this is partial pressure. So if we equal these two equations, we combine, so we will get XA equal XA PA, capital letter P, okay, is equal to YA PP. Okay, we take both equations, okay, because this is the same at the front, the subject is the same, so we combine this equation. Okay, so to get YA, to calculate the mole fraction of A in vapor, which is YA, is also equal to XA PA, which is rearranged divided by total pressure. Okay, so this is will be the equation number 1. Okay, so this is for mole fraction of A in vapor. So for XA, so you take this equation, so partial pressure of A is equal to XA times with the vapor pressure of A at certain temperature. So if you rearrange, so XA is equal to partial pressure of A divided by the vapor pressure of A, pure A at certain temperature. Okay, so the partial pressure of A is also equal to total pressure minus with the partial pressure of B. Okay, and also equal PA, we can also write the as a PA minus PB. Okay, so this is another equation. Okay, this is another equation for XA. Okay, so XA and YA, so if you want to calculate for YB, you just replace A with component B. Okay, so as you can see from these two equations, equation 1 and equation 2, so if you know the total pressure, which is a PP, and the vapor pressure of pure A and pure B, which is PA and PB, at various temperature, we can actually calculate the composition of vapor and liquid. Okay, okay, this is another alternative. If you if for example, if you want to separate a mixture, for example, if you want to separate a component A and B, which has for example A and B, it is very unknown mixture, you didn't get the vapor liquid equilibrium data. Okay, for example, if you open the Paris Chemical Handbook but you cannot find the VLE data for this mixture, so you can actually construct the data, the VLE data, temperature XA and YA. You can use this equation. Okay, so for example, if you have certain temperature, so certain temperature will give you the pressure of pure A and pure B. Okay, from the PA and PB, and if you know the PT, total pressure, you can calculate for XA and YA here. Okay, so this is the alternative on how to get the VLE data. If the mixture haven't been studied yet, and the data has not been tabulated in Paris Chemical Handbook. Okay, so let's do this simple exercise. So calculate the vapor composition, which is YA. Okay, in equilibrium at 368.2. This is temperature for benzene toluene. Okay, for benzene toluene, given that using PA and PB with this value. Okay, so this is the total pressure. So you have PT, you have PA and PB. You can calculate for YA and XA. Okay, so for XA is equal to PT plus PB over PA minus PB. Sorry, minus and minus. Okay, so for YA is equal to XAPA over PT. Okay, you just replace the equation, the value. Okay, PT is 101.32. Okay, you minus with PB is 63.3 kilopascal. So over 155.7 kilopascal minus 63.3, and you will get the value for XA. So for YA, you just multiply the mole fraction here. Okay, you put here and you multiply with the pure pressure of A. Okay, 15517. Okay, you divide by the total pressure 101.32. Then you will get the YA. Okay.